So good morning, everybody. Today, I'm going to talk about some of the work I've done with my colleagues in Toulouse about combining system design and path planning together into a unified framework. So to start with, let's just briefly talk about path planning and a specific subspace of path planning that deals with a cost surface that's superimposed over our workspace. So the goal in that type of scenario is we want to find a minimum cost path from a start state to a goal state. And one of the methods that have been used highly successfully is the transition-based RRT adaptation. And this method has two key components inside of it that differentiate it from normal RRT. One of those is a transition test. So when we go to expand our tree to a new node, we're going to subject that acceptance based on some sort of test. And here on the right, I show you the formula for doing that test. Basically, any transition that's going to move us to a lower cost node, we're going to accept with probability 1. And transitions that are going to have an increased cost, depending on the cost differential, are going to be stochastically accepted. And one of the key parameters in that acceptance test is the temperature, which is the T variable in the denominator. So for higher values of T, we're more likely to accept bigger changes in the cost. So that leads us to the other key component of TRRT, which is the adaptive temperature control. This control basically varies the temperature throughout the exploration to balance exploiting and exploring the search space. So TRRT has been applied to a lot of different problems in both robotics and some in protein modeling. So given this basis, let me talk about another type of problem, and that is actually designing an articulated linkage that will enable us to perform some task with a lower cost. So what I show you here is a simple articulated linkage and a library of alternate components for each of these bodies. The bodies are shown on the top, separated by red circles, which are the common degrees of freedom that are shared across all these bodies. And what this means is I can basically interchange any of the pieces in my database to move into this linkage. Now, in addition to the common degrees of freedom, each of these components have additional degrees of freedom as well. So now let me subject a new goal, which is our new goal is going to be to search both the design space and the configuration space simultaneously to find an optimal design for both the, with respect to the cost of the path. Now, this has applications in robotics, but it also has applications in another area that interests me, which is protein design. So very briefly, let me draw the analogies between these two problems. The first is that we have all these interchangeable parts. Well, proteins which are built out of amino acids actually share a common set of degrees of freedom known as the backbone or scaffolding of the protein. And each of the 20 naturally occurring amino acids actually have their own side chains, if you will, or their own extra degrees of freedom. And it's this difference in these degrees of freedom that play how chemically the protein folds and performs the function that it does. So if I was to be given a start and goal configuration, and also a way to evaluate moving between these start and goal configurations, I could actually use this combined method to now consider alternate designs that optimize the motion I want. And the motion I show here on the right is just a very smooth opening of this lid, which allows different types of protein interaction. So how did we go about doing this? So in this paper, we proposed a new approach that we labeled SDAP, which is the Simultaneous Design and Path Planning Algorithm. It is built off of an extension of the TRRT idea. And what we do in this work is we actually encode multiple designs in each of the nodes of our search tree. So the top shows a typical TRRT search tree, and the bottom you see these different pie cutouts. They each represent a different potential design. So at each iteration of our TR search tree is expanding. So here, our expansion is going to cover at least all the designs in our design space, and I'll walk you through that in just a second. And then we also have to introduce this idea of temperature again, and in our solution, we actually maintain a different temperature for each possible design. So let me walk you through how a iteration of this new algorithm would work. So given the search tree that I've got here, we generate a random node known as QRand, and we are going to locate the nearest node in our search tree to QRand. Now, normally in TRRT, that's all we would need to do. But in our setting, we need to actually try to cover the design space. So what we do is we actually locate the nearest neighbors that cover all the potential designs. And in this case, it takes 3 of them to do that. We then extend each of these nodes towards QRAN, and then we do our transition test. And our transition test, as I've shown here, for the node on the top, none of those 3 transitions were accepted. So we actually are not going to add that search node to our tree. The blue to blue was completely accepted, and the last one on the bottom there, the yellow configuration was accepted, so the new node that's created only has 2 design configurations moving forward. So to test this approach, we needed a simple system that would allow us to baseline this method. So we came up with this articulated linkage, and the design features for this linkage are actually electrostatic charges, where the charges can be positive, negative, or neutral. And we tested this with both a 4-body system and a 10-body system to see how it would perform as we increase the number of degrees of freedom. But both systems we tested have only 4 of the features that are going to be designed. To benchmark this, we used a naive approach, which was basically to brute force our way through all the different designs, 81 of them, and you use normal TRRT, and then we used our algorithm as well. So the last thing I needed to say is how do we come up with this cost? So we use a Leonard-Jones potential, which penalizes objects when they get too close, and we also take into account the electrostatic terms so we can measure how well our design works. And then we use, for determining the cost of a path of the solution, we use this idea of mechanical work, which is that all of the uphill moves or costs that move us up, we count, and downhill motions are counted as 0 when calculating out the path cost. So the problem we designed here, we designed on purpose to favor one design over the other, and you can see the costs maps that are shown here at the bottom. The one on the left has a negatively charged end effector, and the one on the right a positive one, and you can see that for the negatively charged end effector, basically we're moving downhill the whole way, and for the one that's the positively charged one, we're moving uphill. Our analysis showed that on the 4-body system, the red line at the top is the mean of doing the brute force method, and the line green at the bottom shows our method. So you can see that there's some differential. But when we looked at this at the 10-body system, you can see the real power of the method starting to shine through, and that this is almost a 100-fold or a 2 order of magnitude improvement in runtime. So along with the runtime analysis, we also needed to look at the cost of, did it actually find the optimal path? And you can see here, these are all the different design sets going across the x-axis. So there are 81 of them. They're ordered by cost. And I've zoomed in here on that low region since it's kind of hard to see. And you can see that while our method didn't find the lowest cost method, which is shown in the dotted blue line at the bottom, it beat the average performance of doing this brute force, and it also ordered these in almost the same way that brute force search would find. So in a sense, you've limited the number of spaces that maybe you want to search more thoroughly using an extended run of just TRRT. Just to give you a visual example of this is a 5-body problem that we actually worked on. And you can see here, as the mechanism moves, it's a rather cluttered workspace, that the end effector there is negatively charged, and it wanted to stay near the red obstacle that's shown there. But as it moves into the goal position here, you may notice that it turned 90 degrees away from where it was. you can imagine as it got close to the red obstacle there at the end, they would get tracked in a local minima. This would increase the cost of it getting out of it. So in conclusion, let me talk about my dirty laundry, since everybody else has. Our dirty laundry basically consists of the fact that right now we're only able to do this on small 4-5 body designs we've been able to do. We obviously want to extend this so that we can apply it to protein motion and optimizing that. When nodes start to fail in the expansion process, this turns really into a combinatorial search where you can imagine that each of the nodes carry only a single design. And in this case, things break down rather fast. The amount of memory it takes, we're basically would be holding all the search trees simultaneously. And this also has big implications on our nearest neighbor search, which is also a common problem in these types of RRT mechanisms as the search tree grows. So we're entertaining ways of handling this, basically pruning the tree and filtering out different designs that don't show promising, leading to a promising solution. And with that, I'll conclude my talk, and thank you for your attention.
Dimitri is our first responder.
Thanks. Yeah, so really interesting work here. I wanted to ask about the per design temperature parameter. Mm-hmm. And I'm familiar with, in the regular TRRT, how the temperature works and how basically it's a global temperature for the entire C space that determines whether a transition is accepted. But I'm just wondering, in the case of applying it to a design, it seems more acute. The problem of trying to create a global temperature for a single design seems pretty difficult because you're only getting local estimates of whether that design is good for a specific transition, right? And I was wondering if you had any ideas on ways to actually improve that estimate so that in different regions of the space, different designs may perform better, and you kind of don't generalize across all these regions into one number. Is there a way to think about this temperature more locally?
Sure. So that's a great question. In normal TRRT, the temperature is globally, as you said, maintained. And the reason it's not maintained by region, let's just start with the simpler problem, which is just TRRT, is because of the vulnerability basis of the exploration. So we only increase the temperature based on a temperature rate. And the idea being is because of the vulnerability bias, we're going to be expanding the tree in different directions, and we don't really have to worry about this local quantity or quality of the sea space around that area. So in this way, we're kind of doing the same thing, because in the per design, where each design has its own temperature, you can imagine that certain designs are going to expand rather easily, and certain designs are not going to expand rather easily. And since we want our search to encompass searching through all the designs, it kind of makes sense to keep this temperature variant per design. Going back to your question, though, we've thought about doing it locally in these different regions. I actually think there were some reasons that we did not want to do this. Just first, from a theory perspective, I don't think it worked too well. And then from a second perspective, it didn't really give us any better results. But it's an interesting idea, for sure. And maybe there's the right workspace that would would show that would work right.
How do you take distances in this space? Like, in what space is QRAN sampled so as to allow you to take distances from the nodes?
Sure. So QRAN is sampled on the configuration space. So in our body problems that we worked on here, that would be the dihedral angle space between these different end effectors. So basically, it's just the Euclidean distance between those in the angular space.
Does this work for every type of design? And for every
so in this work, where the design doesn't have extra degrees of freedom, so for us, yes. Moving into the protein space, where basically those extra degrees of freedom would impact the cost tremendously, we've looked at what are called rotamer designs, which basically are a discrete representation of the different end effect or the different additional degrees of freedoms and how they're set, and we would evaluate the cost over that space.
Any other questions?
So I'm sort of reminded of a talk at a wafer a few years ago, something searching for an needle in an exponential haystack, in which there was also this sort of property of searching for a path, which is hard, and a design, well, or something exponential, the design in this case.
Mm-hmm.
When doesn't this work? I mean, it's got to not work sometimes.
Well, if the design space is big enough, it turns into a combinatorial explosion and it doesn't work at all. So, when you take optimizing both the discrete and the continuous functions together, there is no, I'm not sure if I completely understand the question that you're asking, but.
Some problems are easy because the rotamers are somewhat local, right? So
Mm-hmm.
they don't really mess up the path
Sure.
globally,
Mm-hmm.
right? So sometimes with rotamers, maybe they're sort of locally just wiggling around and you get one fixed and that sort of helps this part of the path.
Sure.
But then sometimes things are going to be sort of global changes. If I change the design sort of and it moves the whole arm around the other way,
Sure.
it seems like things totally crash. How do you distinguish between these two cases? Other than I ran it, it didn't work.
I'm not sure if I have a real good answer for that question. Obviously, different degrees of freedom are going to have more of a global impact on how much the protein moves and how maybe cluttered the environment's going to get. So minus rerunning it and trying not to run into that stochastically, I don't know of a real good way of addressing that. But interesting thought, for sure.
Thank you.
Okay, you're welcome. Thanks.